In this video, we'll begin to look at another application of the concepts and methods we've learned so far, the process of hypothesis testing. Most of the topics we did at the beginning of this course fall under what's known as descriptive statistics, things like describing the shape, center, and spread of a distribution, and determining the best way to display data. What we're looking at now, though, falls under inferential statistics, in which we use the data we've collected from our sample to make conclusions about the population as a whole. Confidence intervals are an example of inferential statistics in action. What we're going to do now is see another use of inferential statistics, in which we use our data to test an existing claim. Here's a story you may have heard of. In 2013, Australian Matt Corby posted a picture of his foot-long sandwich from Subway, except that it was only 11 inches long. It didn't take long for the photo to go viral, and soon Subway was in the hot seat for potentially scamming its customers. But if you think about it, a single subpar sandwich isn't really sufficient to say that Subway is skimping on its subs. That was a lot of alliteration, but it was a lot of fun to say. Anyway, we've seen just how many things can be modeled as random variables, and sub-sandwich lengths are no exception. Sometimes the length might be a bit less than a foot, and sometimes it might be a bit more. Even if the mean length is about 12 inches, the sample mean might still be a bit less or a bit more. But just how far off is too far off? At what point is a given sample mean so low that it calls the original claim into question? What would it take to show that Subway is most likely cutting corners with its foot-long subs? That's what hypothesis testing is all about. The idea behind hypothesis testing can be broken down into three basic steps. First, we make a hypothesis regarding some claim we want to challenge about a population parameter, such as a proportion or a mean. Then we collect some data, a sample from that population. Finally, we use the data to assess whether we have enough evidence against the original claim. This third step is where the bulk of the calculation happens. And actually, we're not going to focus on any of the calculations in this video or the next one. We'll just be concentrating on the main ideas and how to interpret our results. We'll go into the calculations later. So let's see what this looks like for our foot-long sandwich problem. To begin with, we need to come up with two hypotheses. The first hypothesis is called the null hypothesis, and it states that the parameter we're investigating is exactly what it's claimed to be. It's essentially upholding the status quo. In our case, the null hypothesis is that the average length of Subway's footlongs is 12 inches, exactly what Subway claims it is. Nothing is out of the ordinary, basically, hence the name null hypothesis. We usually use the symbol H0 to represent the null hypothesis. The second hypothesis is called the alternative hypothesis, and it states that the parameter we're investigating is different than the original claim. Usually that's what our hunch is, and therefore that's what we're trying to show. In our case, our hunch is that Subway's sandwiches are actually less than 12 inches on average. We usually use the symbol HA to represent the alternative hypothesis. Take note, the alternative hypothesis is always represented as an inequality, but it doesn't have to always be less than. Sometimes it's greater than if we think the population parameter is bigger, and sometimes it's just not equal to if we're not sure which direction it might be off in. With our hypotheses formulated, the next step is to collect data. Suppose we take a simple random sample of 40 sandwiches, and we find that the average length of all these sandwiches is 11.7 inches, with a standard deviation of 0.6 inches. That's pretty close to the claim 12, but it is still less. The question is it far off enough from 12 inches to make us suspicious of Subway's foot-long claim? That's where the analysis part comes in. To make things more precise, we can phrase our question in terms of probability, like this. If we assume that Subway's footlongs are really 12 inches on average, that is, if we assume that their null hypothesis is true, what's the probability that we'd get a sample mean of 11.7 inches or less? In other words, how rare would our results that we got be? What we need to do is compare that probability, whatever it is, with some level of significance, alpha, say 5%, though we could choose to use 10% or 1% or something else if we wish. And if we find that our results are so rare that they would happen less than that percent of the time, then we'll count that as statistically significant evidence against the null hypothesis and instead toward our alternative hypothesis. It might help to represent this visually. We assume that our data come from some distribution, specifically a sampling distribution like we've been talking about a lot recently. Our level of significance, alpha, is essentially a rarity threshold, sort of a line in the sand that we draw. Once we've decided on our alpha, then we analyze our data and find the probability p that we get a result like the one in our data, assuming the null hypothesis were true. If our p-value, as it's called, is less than alpha, then that means that our results are so out of the ordinary that we think it's more likely that the original claim was wrong in the first place. That means we reject the null hypothesis in favor of the alternative hypothesis. If, on the other hand, the p-value is above our threshold of alpha, then it's not far enough out of the ordinary to conclude that anything is off. That means we don't have enough evidence to reject the null hypothesis. We say that we fail to reject it. Be careful. It's really tempting to say that we accept the null hypothesis. But that's wrong. We assumed the null hypothesis to begin with, and you can't use an assumption to prove that assumption is true. That's circular reasoning. Going back to our foot-long example, if we work it out, we find that the p-value comes out to about 0.00151. Don't worry about how to get that p-value yet. We'll go into how to do that in future videos. Right now, let's just concentrate on what these numbers mean. That p-value means that if the footlongs were really 12 inches long on average, we'd have less than a 1% chance of getting our sample mean of 11.7 or lower. Our alpha level, our rarity threshold, was 5%, and this p-value is way less than that, so we'll reject the null hypothesis. Stated in context, we'd say that there's significant evidence, statistically significant that is, that Subway's footlongs are in fact less than 12 inches long on average. One thing to point out, by the way, our hypothesis test doesn't tell us how much less the population mean likely is. If we wanted to estimate that mean, we'd actually need to construct, you guessed it, a confidence interval. To finish things up, here are a few useful tips for hypothesis testing. First of all, notice that the null hypothesis always uses an equals sign, because it's the status quo claim that we're putting to the test. On the other hand, the alternative hypothesis uses an inequality sign, less than, greater than, or not equal to, depending what our hunch is to the contrary of the null hypothesis. Second, here's a mnemonic you can use for whether or not to reject the null hypothesis. If p is low, reject HO. That being said, it's important to understand why this is the mnemonic. If your p-value is low, that is, less than your significance level, that's saying that our results are so unlikely given the null hypothesis that it leads us to reject it. On the other hand, if your p-value is not low, remember that we fail to reject the null hypothesis. We do not accept it. Next, a note about the word significant in statistics. When we say that we have significant evidence, we're not just saying that we have a lot of evidence or important evidence. Rather, significant specifically means statistically significant. That is, we got a p-value that was less than our significance level, alpha. Finally, and I can't stress this enough, always remember to put your results in the context of the original situation. As a statistician, it's your job to communicate your results in a way that people can understand them. So once you've found your p-value and decided whether or not to reject the null hypothesis, you should always summarize what you've done and what it means for the claim you're actually testing.